Okay. Let me start with a few announcements. There's a homework due today that I'd like you to hand in before the lecture starts. And the solutions are obviously here. You can pick it up on your way out. Announcement number 2 is that there's a makeup lecture on, no, don't pick it up yet. Just come back later. So there's a makeup lecture this coming Monday at 9:30 in this room. This is to, not yet. No, this is at the end of the same thing. There's a makeup lecture on Monday here at 9:30. I'm not sure if there's going to be a live broadcast, but the archives, the digitized version will get posted by the afternoon. It has to be post-edited and re-encoded and all that. It's because it's not a regular lecture. If it doesn't go online by 2 o'clock in the afternoon, could someone please send me an email about it? The course secretary, Rosita Alvarez's office, without any notice to me, just got moved. In fact, it moved on Monday from 558 Corey to 195 M Corey. So you can pick up your graded homework that you didn't pick up from class from her office, and also a copy of the solutions from her office. And the last announcement is that the next homework is due next Friday. Are there any questions or comments? Any issues? Okay. So let me begin today's lecture. What we talked about last time was a bit of difference equations, and also the fact that you can have different, for a given difference equation there can be causal or anti-causal realizations of it, but then once you come up with a given realization, then you can come up with different flow graphs implementing a realization. So just as a quick overview, we talked about direct form 1. If you can zoom in on the camera, this is just last time's lecture. By the way, for those of you in Cyberland who are watching, or there's a lot of people who just find it easier to watch the video of the lecture than the real thing. And some people told me the reason is because if I'm writing too fast or talking too fast, they can pause, rewind, and then re-listen, or just pause to copy. But here's one thing that people hadn't thought about, and that is, if ahead of time, before you even start watching the lecture, you can download and print the PDF. So really, you don't have to copy the notes. You know, the lecture notes go online. The PDF version of this go online within a couple of hours at the end of the lecture. So if I'm writing too fast, which some of you have complained I do, you can get everything I write on a piece of paper on PDF format of it off the web. And B, even if you're not here, you can and you're watching the lecture for the first time, you can print these and don't have to copy as it goes on, and make notes on it if you wanted to as the lecture goes on. So I thought it's obvious, but I just wanted to repeat it so that it makes your life a little bit easier. Okay? So anyway, coming back here, we talked about direct form 1, where the idea was that if you have some sort of an h of z, then the way direct form 1 works is you put the numerator of h of z first and then the denominator later, and this is sort of the structure that you get. And h of z is a system function that's a rational transfer function. Remember, we talked about the fact that for implementing IIR filters, we're the only IIR filters that have can be implemented via difference equations are the ones that have a rational transfer function, right? The rest of them can't. So anyway, and then to arrive at what's called direct form 2, we swap the place of these two boxes. We implement the denominator first, then the numerator. And so here's x of n, here's the denominator, here's the numerator. And if you do that, essentially, this is not the denominator, this is the numerator, then you see a bunch of z inverses being shared by the same signal. So you can collapse these two things and combine them. And if you do that, you get something like this. Okay, so this delay element is not shared between the numerator and the denominator. And what this results in is what's called direct form 2, and it results in minimum number of delays, the hardware pieces of delay needed to implement this whole system. So what I'm going to talk about, are there any questions about last time's lecture or any of this stuff? So what I'm going to talk about now is two other realizations of IIR filters besides direct form 1 and direct form 2. And those are called cascade and parallel. And then you'll see at the end of the day that you can even mix and match these different implementations and realizations to have something that's sort of both, if you will. Okay? Okay, so we're done with, let's start today's lecture. So we're talking about realizations of, or flow graphs, if you will. These are called flow graphs, or realizations of IIR filters with the rational transfer function. Okay, so we've talked about, so far we've talked about direct form 1, then we talked about direct form 2, and now today we're going to talk about cascade structure, and also what's called parallel. Okay. So before talking about the cascade structure and seeing where it comes from and how it works, I'd like to talk a little bit about fundamental theorem of algebra. So remember, before doing that even, let's talk about the h of z's that we're dealing with. These are rational transfer functions, and it's of the following form. There's a numerator, which is the polynomial in z inverse from k equals 0 to q of b sub k, z to the minus k. And then there's also another polynomial in the denominator, 1 minus k from 1 to p of a sub k, z to the power of minus k. Okay? So let's talk for a few seconds about fundamental theorem of algebra. Anybody know what that is?
Every polynomial with real coefficients of degree n has n roots.
It doesn't have to have, that's correct. It doesn't have to have real coefficients. Any polynomial, it says any polynomial in one variable, and I'll explain why we have to say in one variable and what does it mean for a polynomial to be a polynomial in two variables. But it's pretty much what this fellow said, is that any polynomial in one variable can be factored into simple terms, and therefore, if it is of degree n, you can find n roots. Okay? So let's write that down. It says any polynomial in one. You can see that polynomials actually play a pretty important role in a lot of the stuff we're doing. Why? Because you got them. When you talk about rational transfer functions, this is ratio of polynomials, and the reason we're talking about polynomials is because these guys are polynomials. So any polynomial in one variable and I'll contrast it to two variables in just a second, or three, can be factored into simple terms. Okay? In particular, if you have a polynomial of degree n, then it has n real or complex roots, and can be factored into n terms. Okay. So what does this thing really mean? What do I mean by could you have half of that page? Yeah, thank you. So what does it really mean? Well, what it means is that if I have p of z, a polynomial in z, this is a polynomial in one variable. Okay, and let's say, and as an example, it's alpha times z to the third plus beta times z squared plus gamma times z plus delta or something. What it says is that I can factor it: z minus z naught, z minus z1, z minus z2 times a constant. Why? Because right now the z to the power of 3, if I multiply these things out, this is a z. The power of z is, the coefficient for power of z cubed is just 1, whereas the power here is alpha. Okay? So sometimes I put some constant to fix that up. So if you have a polynomial, this is a polynomial of degree n, degree 3. Okay? Then I can factor it into 3 simple terms. Okay? And for polynomials of degree 2, there's an analytical closed form solution that tells you what the roots are as a function of the coefficients, right? What is the largest degree polynomial for which there's an analytic solution for the roots? I think it's 3. Last time I checked, it was 3. Has 4 been invented yet? Or the people who said 4, have they actually seen? Yeah? Yeah, I think it's 3. But anyway, regardless of it, even if you can't come up with a closed form solution for what these roots are, z0, z2, z0, z1, and z2 are, so these are the roots, okay? Those are the places at which the polynomial goes through 0. And we're not talking about polynomials, at this point, we're talking about general polynomials. They could have real coefficients, they could have complex coefficients. And these z0, z1, z2 can be real, or they can be complex. It can be anything. Okay, and the roots are places at which the polynomial goes through 0. And if the polynomial is of a large degree, let's say 10 or 20 or 50, there's always numerical methods of finding the roots of it. Can anybody say what those methods are? An example of it. Secant method. Can you say a few? Whoever who said it, can you say a few words about it?
Well, I guess every time you have an estimate for the root from this place, you draw a secant, and it gets closer and closer.
Okay. Good. Another technique is Newton-Raphson. They're all iterative methods of finding roots. Okay. By the way, while we're at the subject, it's a slight deviation from what we're talking about, but the problem of finding roots of polynomials is an ill-conditioned problem. What's the meaning of an ill-conditioned problem? It's a problem in which the solution is extremely sensitive to the input data. It means that if you perturb the data a little bit, the solution changes a lot. That's an example of ill-conditioned problem. I'm not talking about ill-conditioned algorithm. That's a different thing. There's a thing, I don't know if have I detoured into the explaining what an ill-conditioned problem is versus an ill-conditioned algorithm? Have I talked about that already at the beginning? Okay. It's a pretty important concept, and it's used in signal processing all the time. So there's a thing called a problem. The input data goes into it, and the solution or the answer comes out of it. So for example, if I'm solving the problem of finding roots of a polynomial, the coefficients of the polynomial goes into it, and out come the roots. Okay, so this is the problem of finding the roots of a polynomial. And what I'm saying is that this problem is extremely ill-conditioned. So the problem is ill-conditioned if small perturbations in the input result in large changes or perturbations again in the answer or in the solution. Okay, so for example, as it turns out, the problem of solving finding the roots of a polynomial is an ill-conditioned problem. If I change the coefficient by like 1%, the roots change by like 20 or 30%. And there is actually a definition of what's called a condition number of a problem, which tells you the relative change in the answer compared to the relative change in the input data. So if I change the solution by 1%, the answer changes by 10%, the condition number of that problem is 10. If I change the input data by 1% and the answer changes by 100%, the condition number is 100, something like that. So some problems are inherently, regardless of what algorithm you use to solve them, they're inherently ill-conditioned. Okay, and the problem finding roots of a polynomial is an inherently ill-conditioned problem. It doesn't matter what algorithm you use, secant, Newton-Raphson, whatever. The answer changes a lot by changing the input. Can you think of another problem that's inherently ill-conditioned? Weather forecast. That's the classic. You can only predict 2 or 3 days from now, or maybe at most a week from now, because you need to compute the initial condition of what the temperature and the pressure distribution is extremely accurately. You need to, in order to be able to forecast, a month from now. So, as long as there's a little bit of an error, just let's say the temperature is, 75 degrees. If it was 75.0001, if it was something different, the answer changes quite a bit. So for that reason, the problem has always been ill-conditioned. Okay, that's why we can only forecast, at most a week from now. And why is an ill-conditioned problem bad? Well, 2 reasons. One is that you need to compute the coefficients or the input, the input to that problem, extremely accurately, and there's always measurement noise, instrument noise. And if it is not instrument noise, round-off noise, when you're crunching numbers on the computer, as I'll talk about finite precision in the next lecture, the computer has only finite precision. So the errors introduced in the computation acts as if the input was slightly perturbed, and that causes the answer to be changed a lot. Okay? So there are some problems in the universe that are, inherently ill-conditioned. Now, let's talk about algorithms being ill-conditioned or well-conditioned. So for a given problem, okay, so the upshot of this, let me write that down. So some problems are just fundamentally ill-conditioned. It's called ill-conditioned. Okay, and there is a thing called the condition number for a problem. Okay, so now I'm going to switch gears and talk about algorithms. And what do I mean by that? For a given problem, there could be multiple algorithms to solve it. It could be algorithm 1, algorithm 2, algorithm 3, algorithm 4. And can you think of a problem that has 4 ways of getting solved? Let's say, I want to solve a linear system of equations. I mean, there's got to be a million ways of solving it, right? Can anybody name one? Get a matrix, write it in matrices, invert the matrix, and then multiply. Okay, so let's call it invert the matrix. What other ways are there of solving it? Good. And there's 2 ways of doing it. Within Gaussian elimination, what are the 2 ways? Exactly. So there's Gaussian elimination with pivoting and without pivoting. And what else is there? Gauss-Seidel. Gauss-Seidel, okay. What else is there? QR decomposition. Don't worry if you don't know all these things. This is a linear, they're all in linear algebra. But of all these methods, in fact, I'm so glad somebody talked about Gaussian elimination. Why do you think pivoting was introduced in Gaussian elimination? Because Gaussian elimination without pivoting is a terrible way of solving linear system of equations, because even though your problem, so here's the difference between the problem being ill-conditioned and algorithm being ill-conditioned. If the problem is ill-conditioned, you're sort of stuck. That means there's no algorithm you can find to give you a good, nice, stable answer. If your problem is well-conditioned and you apply an ill-conditioned algorithm, you still are in trouble, because then you're getting wrong answers or extremely sensitive answers. So it's very important that for a well-conditioned problem, you have good algorithms. And an example of a bad algorithm, there's two of them here. What do you think are the two techniques that are two algorithms that are ill-conditioned? Bad ways of doing it. This is terrible, and without pivoting, that's also terrible. And I can tell you QR decomposition is extremely good. Okay? So the upshot is that even if a problem is well conditioned, okay, if you applying an ill-conditioned algorithm could destroy your answer. In other words, could make your answer to be extremely sensitive to the input. Can make the answer be sensitive to the input. Okay, so you know, the problem being ill-conditioned is sort of God-given. You can't do much about it. But if you got a well-conditioned problem, you better choose a technique that's stable and good. And that's why in the numerical linear algebra literature, there's so many different ways of solving linear system of equations. Not that we are. So this is solving linear system of equations. This was our example of having these 4 different methods. Now, just while that we're on it, can anybody say, if you're solving a linear system of equations, can anybody say what's the condition number of that problem? No, you're close. But so what you do is you have linear system of equations AX equals B. A is a matrix, X is a vector, and B is a vector. X is your unknown. So you apply SVD, singular value decomposition, to A. Again, if you don't know what that is, that's okay. And the condition number of that problem is the ratio between the largest singular vector value over the smallest singular value, sigma max over sigma min. Okay? So if I gave you, so even for a linear system of equation, I can give you A's for which the ratio between sigma max and sigma min is very, very large. In that case, you already have an ill-conditioned problem in your hand. But if you want to know how well conditioned your problem is, you just compute this ratio. And what would be, intuitively speaking, what's an example of a matrix, for example? What can we say about the matrix for which sigma max over sigma min is very, very large, in a million, 10 million, a billion? It's a near singular matrix. The rows of it are almost dependent on each other. They don't have matrices that don't have full rank, that are near, I mean, this notion of, does everyone know what full rank means? This notion of full rank versus not having a full rank is not a binary thing. Oh, this is full rank, this is not. You know, it's a gradual thing. You can have a matrix, yeah, I mean, if you have a matrix and you repeat one of the rows identically to the next row, yeah, obviously you've already made it lose some rank, right? Rank by 1. But you can also be, you cannot repeat that row, but make it really close to the previous row. In that case, you've made it nearly singular, nearly lose its rank. So this quantity here is sort of a measure of how ill-conditioned your matrix is, and all those other things. Okay, so this was a detour. I mean, it has nothing to do with realizing filters or any of that. But in a lot of signal processing problems, if you have a well-conditioned problem, it's important to develop algorithms that don't destroy the problem, that are well-conditioned. So how do we get sidetracked into all of these things? we got sidetracked because we're talking about polynomials and roots and fundamental theorem of algebra. So we're talking about the fact that fundamental theorem of algebra, it says that a polynomial in one variable can be factored into simple terms, and that's what it says. So if I have a polynomial of degree n, I can factor it into n terms. And what I was trying to say, the reason we got sidetracked into all these discussions, is that if you have a polynomial of degree 100 or so, then you have to factor this thing. It's a pretty ill-conditioned problem to try to find all the 100 roots, but that's beside the point. But fundamentally, you could factor it. Okay. However, the reason I emphasize, could you zoom up, please, just a little bit? The reason I emphasize this one variable thing here is because if you have, and this fundamental theorem of algebra actually does not hold in larger dimensions than 1 when you have polynomial of 2 or 3 or 4 or 5 variables. So this is something to note, is that fundamental theorem of algebra does not hold in 2, 3, or higher number of variables. That means that if I write a polynomial p in terms of z1 and z2, let's write, it would be alpha times z1 squared plus beta times z2 squared plus gamma times z1 z2 plus delta, or something like that, plus epsilon times z1 plus, I ran out of letters, eta times z2, all these things. You can't necessarily factor these. And it's not because we don't know how to factor it, and tomorrow morning somebody will wake up at the other corner of the world and will tell you that, oh, I figured out a way how to do it. In fact, that's not it. There's a proof that says that most polynomials of degree 2 or higher are not factorable. Okay? So the theorem says most polynomials in 2 or more variables are non-factorable. Okay? And we'll talk quite a bit about that in E225B. And one of the consequences of this is what? Well, if you have IIR filters like this, one of the issues you always care about in designing IIR filters is stability. Why don't you care about stability when you design FIR filters? Because the definition of stability, that's correct, is that the h of n has to be absolutely summable. In other words, you add up absolute value of all the h of n, it has not to blow up, right? And if you have finitely many terms, you add finitely many finite numbers, it could never blow up. When you have an IIR filter, you have infinitely many terms, and it could blow up. And if you wanted to have a causal IIR filter, we want that pole to be where? If you causal IIR filter, that's stable. That's what I'm trying to say. You want the pole to be inside the unit circle. And how is it that the fundamental theorem of algebra can help us verify that? If I give you an h of z that looks like this, fundamental theorem of algebra says you can factor it out. You know exactly where the poles are, right? The fact that you can factor it, it tells you exactly where the poles are. And then it's so trivial. You look at each one, and if the magnitude is smaller than 1, it's inside unit circle, and you're all set. So therefore, one of the nice consequences of fundamental theorem of algebra in 1D is that you can check stability very easily. You just factor the polynomial and you're done. The denominator of h of z and you're done. However, in 2D, the fact that you can't factor these things makes it very difficult to check stability of 2D IIR filters. And I dare to say that's the reason IIR filters are almost never used in 2-dimension. Okay? So it's not that we didn't figure out a way to factor these polynomials, but in fact it's true that most polynomials in 2 or more variables are non-factorable. And in fact, if I was going to say this theorem in a more precise term, I would say that the set of polynomials in 2 variables that are factorable are of measure 0 among the set of all multivariate polynomials. Something being a set of measure 0, it's again a mathematical term. That means if you randomly choose polynomials, the coefficients of it, the probability that you pick one that's factorable is very, very, very small. It's close to 0. That's what that means. So one consequence of this thing, as I said earlier, is that you cannot check the stability of IIR filters in 2D easily. However, the 1D result enables you to factor the denominator of your h of z. So if it is p of z over q of z, and that way you know where the poles are, and as long as they're inside unit circle, then you can check stability very easily. Okay. Okay. So so enough of a detour in that. So what does all of this have to do with realizations of cascade structure? Well, I want to say one more thing before I talk about cascade structure, and that's a follow-on to fundamental theorem of algebra, and it goes like that. It says that if the coefficients of this polynomial, and for now we're just dealing with in one variable because that's the only hopeful situation. The other situation is pretty much hopeless. Are real. What can we say about the roots of that polynomial? Pardon? Somebody said something. What can we say? What statement can we make about the roots?
They're real or complex conjugates.
That's right. Then the roots are either real or they are complex conjugates. Okay. What do I mean they're complex conjugates? That means that if the polynomial has a root that's complex, it has to have the conjugate of that also at its roots, given that its coefficients are real. Okay. And that means that it implies that if z naught is a root that's complex, that's not real, then it must be that z naught complex conjugate is also a root. Okay. So what does all of that imply about roots of polynomials? So let's start with polynomial of degree 2. Alpha z squared plus beta z plus gamma. What are the possibilities in terms of if again we're assuming gamma and alpha and beta are all real? What are the possibilities for the roots of its polynomial of second degree? There's two roots for one thing. Either both of them are real. Okay, so either both real. That's possibility 1. Possibility 2, if it has a complex root, then the second root has got to be conjugate. So, or it has a pair of complex conjugate poles. Okay? Everybody sees why that's true? That comes straight from this statement here. What can I say about the polynomial of degree 3? Let's say alpha z cubed plus beta z squared plus gamma z plus delta. What can we say about its roots? What are the possibilities? Well, one possibility is just if we know the coefficients are real again. One possibility is that all three roots are real. Okay? And what's the other possibility? Maybe one of them is real, and then two complex conjugate pair. And is there a third possibility? No, because if two of them are complex conjugate, the third one cannot be complex. Because if it was complex, its conjugate should have been also the root, so it just can't happen. And how about a polynomial of degree, let's say 4? What can we say about that? Case 1, you can have 4 real roots. Case 2, you can have 2 real roots and 1 complex conjugate. And finally, case 3, you can have 2 pairs of complex conjugate pairs. Okay. And it goes on and on and on. So is there a trend to be seen? Yeah, I think if the polynomial has an odd degree, like 3 or 5, it always has, it has real coefficients. What can we say? It always has a real root, right? It's always going to have a real root. So one of the trends that comes here is that if the polynomial with real coefficients is of odd degree, then it always has a real root. Okay. By the way, yeah. So, question, yeah.
What if we have a root with multiplicity 2? Like if we have a complex root with multiplicity 2, then isn't it possible that the complex conjugate also exists?
And has multiplicity 2, yeah.
Oh, they both have
Yeah,
multiplicity.
right. So, why did I write all of these things? Well, because I wanted to come up with a general expression or form of factoring this h of z, which is ratio of two polynomials. Remember that we started off the lecture by assuming our h of z is of this form. I want to write up a general form of for these polynomials. Okay. So my claim is that based on this little detour that we went about, polynomials of degree 4 have what form, and etc. So my claim is as follows: is that if I have for a polynomial with real coefficients, I can using all these arguments that I just talked about and fundamental theorem algebra, I can write, or I can factor it in the following way, this way. Okay, so if I have P of z with real coefficients, then I can factor it as having a bunch of real roots and a bunch of complex conjugate roots. So it will be a product of a bunch of real roots, 1 minus c sub k z inverse, okay, where c sub k is real, times a product, this is a product symbol, a bunch of terms that are complex conjugate, 1 minus dk z inverse times 1 minus d sub k complex conjugate z inverse. These are products, okay, where d sub k is complex. So in its most general form, if P of z is real coefficients, because of the statement that I just made, either it has real roots or it has complex conjugate roots. So I can write it like that. Okay. So that's a direct consequence of the factorization and other things that we talked about earlier. And therefore, given that, I can now write my h of z, the good old h of z from the beginning of the lecture, as summation from k equals 0 to q of b sub k z to the minus k over 1 minus k from 1 to p of a sub k z to the minus k. I can write it in the following gigantic form. It's some constant, and then it's a ratio of two polynomials. So I write a polynomial like that for the denominator and another polynomial like that for the numerator. So the numerator, for example, would be product over k of 1 minus e sub k z inverse, where e sub k is real, times the product over k of 1 minus f sub k z inverse 1 minus f sub k complex conjugate z inverse over product over k of 1 minus c sub k z inverse, and then product over k of 1 minus d sub k z inverse times 1 minus d sub k complex conjugate z inverse. So e sub k is real, c sub k is real, and f sub k is complex, and d sub k is complex. Okay, so this is the most general way I can write my h of z. And I put an a here because if I multiply all these things out, the coefficients of my constant term is 1 Please turn your cell phone off before class starts. And the A here makes sure that you can have an arbitrary scaling factor here. Okay? So now, having put it in this general form, I'm going to go one step further, and I'm going to write down this term, or equivalent to this term, the product of the complex conjugate. I'm going to multiply that out. And so that I end up having a second-order polynomial with real coefficients. That way, I have real coefficients flying around everywhere, and I don't have to deal with complex arithmetic, complex numbers, complex anything. So what I'm going to say is the following. Note that if 1 minus d sub k z inverse times 1 minus d sub k z complex conjugate, I'm sorry, d complex conjugate z inverse, which is this thing, can be written as what? Is the same as 1 minus 2 times the real part of d sub k z inverse plus magnitude of d sub k squared z to the minus 2. So now this is a polynomial now with all real coefficients. Why? Because this is real, the real part of something, even though that thing is complex conjugate is real, and this thing is real. Okay. And so then equivalently I write this down as 1 plus, just to make my life easier and not to have to carry this long notation, beta 1k z inverse plus beta 2k z to the minus 2. And this is real, and this is real. Now I've just renamed this thing. Minus 2 real part of d sub k, I just called it b1 beta 1k, and d sub k squared, I called it beta 2k. Okay? Alright, so now what can I say? Well, I can say that I can rewrite this expression I have up there as the following. I can say h of z is just a times product of a bunch of simpler terms, which I call h sub k of z, where h sub k of z takes on this general form. Okay, it has it's sort of a general form of, and I know that previously I had first order terms and second order terms, but a first order term is a second order term, is a special case of a second order term with one of the coefficients set to 0. So I'm just going to write h of z as a product of a bunch of second order terms. And what are those second order terms? It's these guys. 1 plus beta 1k z inverse plus beta 2k z to the minus 2. And again, if beta 2k is equal to 0, I get a first order term, which would have been one of these guys. Simple zeros, right? Over 1, another second order polynomial with real coefficients, 1 minus alpha 1k z inverse minus alpha 2k z to the minus 2. It becomes clear why I chose negatives, but it's besides the point. Is this last? I see a lot of confused faces in this last step. All I'm saying is that h of z was the product of these guys, right? I have second order terms, second order polynomials, and first order polynomials. But I'm saying is first order polynomials is the same as a second order polynomial. Each one of these terms is a second order polynomial with real coefficients, right? Each one of these terms is a first order polynomial with real coefficients. But I'm saying a first order polynomial with real coefficients is a special case of a second order polynomial. So I just write down h of z as a product of first order product of second order polynomials over another set of product of second order polynomials, where sometimes the coefficient of a second order polynomial is 0, thus making it a first order. Is that clear? So that's what this thing is all about. It's just a product of terms like this. And these alpha 1k's and alpha 2k's, they're all related to these dk's and ck's and all these other things. Okay? So most generally, I can write h of z in this manner. And then pictorially, what's really happening is the following. So I have h of z implemented as follows. X of n goes into it, and then it goes to h1 of z and h2 of z, da 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 da, all the way to h sub m of z, and out comes y of m. Okay? So this implementation, or this expression here, is called cascade implementation, because it's a so this is called cascade because it's a cascade of a bunch of simpler second order systems. Some of these are second order systems. I mean, some of them have polynomials that are second order, some of them have first order, but they all have real coefficients. Okay, so here these are all real. Okay? So now the questions that then arises, okay, you know, I just converted the problem into something else, but it still didn't tell you what the flow graph for this whole system is. I just decomposed it saying it's a cascade of a bunch of other things. And so the answer is that let's just talk about implementing one of these, any one of these h sub k of z. So question is how to implement any one of these h sub k of z's. In particular, this one that's shown here. How do I implement that? Well, it's your call. You can use direct form 1, you can use direct form 2, or anything you like. So because direct form 2 uses fewer delays than direct form 1 does, so let's just, for the hell of it, use direct form 2. So here comes x of n, and what's the implementation of this guy here? Well, it's a special case of what we derived in last time's lecture. Here's the delay element being shared, and here's beta 1k, and here's alpha 1k, the arrow going this way, and things getting added up there, things getting added up there, and then one more delay, which is z inverse, and then the arrow going this way, alpha 2k, beta 2k. So this is how a particular h sub k of z is implemented. And again, either any one of these alphas and betas could be 0, right? Staring at this thing over here, if beta 2k is 0, then the numerator becomes first order. If alpha 2k is 0, then the denominator becomes first order. There's a liberty to make any of these things equal to 0. So this is it. This is a cascade structure. You start with the h of z, and you factor everything out, and then you implement it like that. So this happens to be, we chose a direct form 2 implementation of h of the k of z. You could have chosen anything you like. So as an example, let's just give you a concrete example so you can see what a cascade structure of some filter would look like. So suppose I have h of z equal to 1 minus z inverse over 1 plus half z inverse 1 plus z inverse plus 1 half z to the minus 2. So somebody already gave you things in a factored form. So then I can write it as 1 minus z inverse 1 plus 1 half z inverse 1 over 1 plus z inverse plus 1 half z to the power minus 2. So how would the flow diagram of this look like? Well, it's h of z equals h1 of z times h2 of z, where h2 of z is this guy and h1 of z is that guy. So let's just do it. So here, I'll use a new sheet because the picture is, well, I think I can squeeze it in here. So here's x of n coming in. How do I implement h1 of z? Well, it's h1 of k, but remember this is the expression for h hk of z that corresponded to this system had this expression, right? Let me just repeat that here so that it's all in one page. It's 1 plus beta 1k z inverse plus beta 2k z to the power of minus 2 over 1 minus alpha 1k z inverse minus alpha 2k z to the power of minus 2, right? That's the expression for hk of z that corresponds to this. So now, putting all these things together, can you go up just a tiny bit so that this and this can be shown? Great, thank you. So, yeah, so staring at this and staring at this and staring at that, what h1 of z is the same as this expression, but except beta 2 is 0 and alpha 2 is 0, right? Because the numerator is first order and the denominator is first order. So if beta 2k is 0 and alpha 2k is 0, these two branches just get eliminated, so I only get the top two pieces. And for this expression, what's the equivalent for my beta 1k? Look at this and look at this. What would be my beta 1k to implement this? Is it too simple, or are you not following? Too simple. Okay, good. I never know. I mean, somebody should answer so I know which end of the spectrum I am, right? So it's minus 1, correct. And what's alpha 1 of k? Minus half, right? Because it's the coefficient of z inverse, and coefficient of z inverse here is half. So minus alpha 1k is half, so alpha 1k is just minus half, right? So this is the same as that, so the flow diagram I have here is exactly this with these two guys set to 0, so those are gone. Alpha 1k equals 1/2, beta 1k equals minus 1. So let's do that. Let's draw that. Boom, 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 boom. Z inverse coming here, arrows going that way, arrows going that way, and we just decided alpha 1k is minus 1/2. And beta 1k is also minus 1. Okay? So this implements our h1 of z, which is this guy. And now I have to implement h2 of z, which is this guy. Now stare at this h2 of z, which is this guy, and the expression we have for hk. What can we say about beta 1? So the numerator now is of just degree 0 in z. That means beta 1k is 0 and beta 2k is 0. So that means these two pieces are gone. Boom. Okay? Right? And what else can we say is that, stare at this one, alpha 1k, which is the coefficient of z inverse, is minus 1, and alpha 2k is minus 1/2. Right? So just redraw that with these gone, and alpha 1k minus 1 and minus half. So let's just do that. So let's repeat that structure. So that would be boom, 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 and these are the two delay elements, Z inverse, Z inverse, and the arrow goes this way. And then the arrow goes that way, and we just decided alpha 1k is minus 1/2, and alpha 2k is minus 1, and this is minus 1/2, and out comes y of it. So this is the cascade structure implementation of this system. Okay. So just staring at this thing now, is it, as a side comment, is it losing, so this was our h1 of z, and this is our h2 of z. Now, how many delay elements did we end up using in this? 3. And what would the direct, if we were going to implement this in direct form 2, what would be the direct form 2 number of delay elements in that case? 3. So did we exceed? No, it's the same. So that's pretty good. So so we're still doing pretty nice. Okay. Okay, that's the end of my discussion on cascade structure. Are there any questions? Yeah.
What's the advantage of the cascade system? Why do we have it?
I'll talk about that a little bit after I've talked about the parallel structure. One advantage is that it's somewhat robust to the location of the roots, more so than the other forms are. So I'll talk about that at the end of the discussion. Okay. Yeah, one more question.
You can only use it if you have real coefficients.
Yeah, the question was, you can only use it if you have real coefficients. Well, in this development, I assume real coefficients so I can factor everything nice so that all these coefficients of these HKs are all alphas and betas are all real. If they weren't real, I could still factor them out, and I could still, I could still have, once I factor them out, I can put them as a cascade of the factored terms. It wouldn't have real coefficients then. Or it might have some real and some complex coefficients, but it'll be complex arithmetic in general. See, the idea is that if you have an h of z, which is ratio of polynomials, if the coefficients of these polynomials are real, that means the coefficients of the linear constant coefficient difference equation that you have is also real. So most times people are, if your application makes those coefficients automatically real, then the coefficients of these will be real. And so a lot of things simplify in a nice sort of way. But if it was complex, all of these things holds true, but everything would just be complex. Okay. Any other questions? Okay. I want to make one more comment. I mean, again, it's unrelated to filter design, but I think it's a pretty interesting one. And that is one of the other consequences of fundamental theorem of algebra in 1D, and the fact that it doesn't hold in 2D. The reason I want to make this comment is because it relates to my own PhD thesis about 15 years ago. I always make that in this course, is that one of the consequences of fundamental theorem of algebra is that if you have a polynomial, if you have a curve for a polynomial of degree n, okay, as a function, let's say it's p of x, right? If you sample this thing at n points, any n arbitrary points, okay, you can recover the coefficients of that polynomial. This has nothing to do with real, complex. This could be z, this could be complex. If you have n arbitrary values of a complex polynomial of degree n, you can uniquely recover the coefficients. And how would you recover it? Can anybody quickly think of a quick scheme to recover the coefficients? So you know that at location z0, it took on the value alpha naught. At location z1, it took on the value alpha 1. At location z2, alpha 2. How would you quickly find the coefficients of the degree polynomial then? Yeah, you set up n equations and n unknowns, right? So you would say, let's say the polynomial with p of z was, beta n z to the n plus beta n minus 1 z to the n minus 1. So you just plus da 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 beta 1 z plus beta 0. So you plug in z equals z naught into this whole expression, and the right hand side becomes alpha naught. Then you plug in z equals z1, the left hand side becomes z1. So you end up having a linear system of n linear system of equations with n unknowns. The unknowns are beta n minus 1, beta 1, etc., etc. And having a linear system of equations with n unknowns is the same as solving ax equals b. And how do you find x? You have A is an n by n matrix. How do you find x? Any of those 4 techniques we talked about. Hopefully you pick a well-conditioned one. And what's the name of that? And one of the consequences, what I'm trying to say is that what is the danger in solving this linear system of equations? Every time you solve a linear system of equations, what's the biggest danger you face off? Singularity. You always have to worry about that. I know you have other things to worry in life besides singularity, but that's what every time you see if you're working in this field, every time you see it, you have to solve a linear system of equations, or it's just singularity, because if it's singular, that means you can't find a solution. It's got infinitely many solutions, okay? But what I'm trying to say is that what fundamental theorem of algebra guarantees is that A is never singular. In fact, A is a special kind of matrix. Why? Because it comes in, because the way A is formed is, let's say it's Z naught to the n, Z naught to the n minus 1, Z naught n minus 2, da 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 da, Z naught squared, Z naught, and then 1. Or yeah. And then the next row in it is Z1 to the n, Z1 n minus 1, Z1 n minus 2, da 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 da, Z1 1, etc., all the way to Z sub n, I guess. To the n, Z sub n, n minus 1, da 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 da, Z sub n 1. So this matrix, the A matrix, for if I sample this thing at random, it's not equally spaced, but it's just random, whatever your heart desires. You can have two close to each other, then far away, etc. You get this matrix, right? And this matrix has a special structure. And because of the special structure of it, fundamental theorem of algebra guarantees that it's always non-singular, which means that you can always find the coefficients by having n random samples. And what's the name of this matrix? Anybody know that? Vandermonde. Okay? So all of these things happens beautifully in 1D. And then when you go to 2D or higher, it falls apart. So, and what does that mean? It means that in 2D, because fundamental theorem of algebra has been shown not to hold, it's not that we didn't prove it yet, somebody might prove it tomorrow, it's been proven it doesn't hold in 2 or higher dimensions. In 2D, if I have a polynomial of Z1 and Z2, here's Z1, here's Z2, some polynomial is sticking out of this plane, and I just go ahead and sample it. You know, let's say it's P of Z1 and Z2, it's something of second degree, or it's, you know, it's alpha Z1 square plus beta Z2 square plus gamma Z1 Z2 plus epsilon Z1 plus eta Z2 plus delta, etc. So it's got 1, 2, 3, 4, 5, 6. So if I go and sample it at 1, 2, 3, 4, 5, 6, and try to solve the same things, I cannot be guaranteed the matrix is non-singular. It might be. There might be some combination of 6 points, locations that might make the singular non-singular, but there's no guarantee. In fact, I can come up with I can pick my points in such a way that I make it non-singular. So, for example, if I put them all in a line, like that, straight line, etc., you can show that this becomes singular, and sort of you're in trouble. So none of these results in 1D holds true in 2D, and so in particular, reconstructing 2D polynomials or 3D polynomials from their arbitrary sample is not a solved problem. You could run into singularities if the geometry of your points is chosen in a pathological. It's chosen not carefully. And actually, what my PhD thesis addressed is how to pick these points so that you're guaranteed not to run into singularity. It turns out that if you make them on what's called on irreducible curves, curves that cannot be factored, and put the right number on the right number of curves and do this and that and the other, then you can uniquely recover the coefficients of these polynomials. Having said all of that, let me just say one last thing. The way to make this thing run into singularities is if you put these points in a special sort of geometry. So another result in my thesis was, if you really honestly truly pick these randomly with no particular structure, the number of times you run into trouble is of measure 0 among the total number of times you try it. So it's a game, right? You throw these randomly, you repeat this experiment 1 billion times, this result says that if you truly do it randomly, the number of times that you run into singularity is of measure 0 among this 1 billion times that you do it. Okay. Okay, enough for PhD thesis. Now let's go back to real life. So I'll say like few words about parallel implementation. So, okay, not at now that, so once again we're starting with this h of z guy, which is the summation from k equals 0 to k of b sub k times z to the minus k. And the denominator is 1 minus k from 1 to p of alpha k, no, a sub k, sorry, z to the minus k. And we already wrote that down in this other form with all these, where is it now? Yeah. We already wrote that down in this, funny forms and all kinds of things. And so, what parallel implementation, so I'll just put that up here if you can zoom up to the half, yeah, so we already wrote that like this. So, what parallel implementation says is that instead of writing it as a product of terms, just write it as sum of a bunch of h sub k's. Here we wrote h of z as a product of a bunch of h sub k's. And now in parallel you write it as a sum. So I'm going to write it as a sum over k of, let's say, a sub k z to the minus k. These are, if the numerator was had a higher degree in z inverse than the numerator, a bunch of these things come out, plus a bunch of simpler terms, summation over k of b sub k 1 minus g sub k z inverse plus summation over k of c sub k plus d sub k z inverse over 1 minus h1k z inverse minus h2k z to the minus 2. So what's this whole thing is all about? Is I'm just writing h of z as a sum of three kinds of systems, right? I'm writing it as a bunch of sum of a bunch of systems in which the numerator, is of this form. There's no denominator. It has 5 times e to the minus 3 plus. It's the same way as you do partial fraction expansion on things, right? A bunch of simple order terms and a bunch of, first order terms, and a bunch of terms where the degree of numerator is 1 and the degree of the denominator is 2. Okay, this is the most general form you can write each h of z in. If, in particular, if I give you an h of z where the degree of numerator was smaller than denominator, this wouldn't exist. Then you could write it as the sum of these two things, right? So, can you see where you go from here to here? It's simply partial fraction expansion. Divide the numerator over the denominator, get these terms, and then do partial fraction expansion. That's all there is to it. Okay? So where these guys are real, and these guys are real, and these guys are real, the reason is because we have these second order polynomials that have real coefficients and all. Okay? So, okay, is this step clear? Maybe I should do. Yeah, I'll do an example to see how you got from here to here. So then in that case, then you can write your h of z essentially as a bunch of sum of h sub k of z's. Okay? So x of n goes in, and you have h of 1, and then h of 2, all the way to h sub m of z. And then you add these things up. And out comes y of n. So that's why it's called parallel. It's almost like series and parallel that you learn about lamps and electricity or something when you were in high school. But here's an example to sort of clarify that just a little bit. So if I have an h of z which is given by 2 times z inverse plus 1 minus z inverse over 1 plus z inverse plus 1/2 z to the minus 2. So I start with x of n. So first I want to implement this system. So I go up here. You multiply it by 2, you get, and then you delay it by z inverse. So this is it. And then I implement this other system, and for this system, I can do direct form 2, because that's a nice efficient thing. And how do I do the direct form 2 for that? Well, I have a generic second order direct form 2 sitting somewhere here, right here. Remember this picture? So if I do that, if I look at this expression here and look at that expression, so the numerator is of degree 1. So beta 2k is 0, so that's gone. So it'll look like it'll have this branch, and this branch. So let's just do that. So it'll have these branches. Okay? So let's put z inverses all over the place, and staring at these simultaneously. So beta 1k here is minus 1, so let's make that minus 1. Alpha 1k is minus 1, so that's this one. And alpha 2k is minus a half. So this thing is implemented as this, and so this out comes this, and then you add these guys up, and out comes y of n. So you can also mix and match these things. So you can also write down, depending upon how things work, you can write down h of z as a cascade and parallel structure. So it's the summation over k of h sub kz plus some product of terms, summation product of k g sub k of z. So here you're mixing and matching parallel and cascade, and the block diagram for something like that would look like this: x of n coming in, h of 1, h of 2, and then g1, g2, da 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 da, g sub m. And then out comes y of n. So here's the cascade part, and here's the parallel part. I'm going to stop now, but I'll talk a little bit about quantization characteristics of these four different schemes on Monday, and then I'll also talk about what's called transposition theorem, and that brings us probably maybe by the end of Wednesday. That brings us to the end of chapter 6. And then we'll move on to the discrete Fourier series and other stuff. See you all on Monday. Oh, don't forget to pick up the solution on your way out. Let me just put half of it over this side. Put it on the table. So
I found 2 errors in this.
Why don't you catch the errors ahead of time? I mean, this is very good. Is this because this is a copy of Quran?
No, this is, I did this.
You did this yourself. Okay.
But just the magnitude.
Okay, why don't you put the errata on the
Yeah,
bed?
I can do
That's easier. That's a lot easier.
Okay.